gonna work out. I'm gonna have to take medicine, but every year I'll have like two electives, two or one elective. Yeah. I can't fill my entire schedule at 5 o'clock, and just do the rest of the school. I could drop courses very beginning because I didn't learn it. I didn't learn it all. Yeah. And I didn't think that I was going to do it enough on final and keep started. I'll let you do it. Yeah. I'm not saying about people. Well, crap. I definitely done that before. I can handle it. Yeah. Like the first 2 years of having not engineering difficult advisor is not. Oh no, not at all. If you don't know any of the classes are like, they're just looking at like, oh, if you need this, and you need this, and you need this, and then I invested like this is really mechanics and gear at the same time as dying and slow, and I start out the time before. Like 3 hours. For what? Oh, for now? Yeah. I feel like that wasn't true. That's ridiculous. Nobody has like doing transition time. Well, because what, you're in like 15 to 18 hours a semester, so you multiply by quote unquote 60 plus hours a week. Yeah. But you spread that out. You know, time. Yeah. People can't do it. Yeah. Or eventually move it to the 5 years later. Yeah. It's really worth it.
All right, so let's see. Do y'all have any? Sorry, do y'all have any questions up to this point? Oh, that's hand sanitizer. If you don't, oh, go ahead.
These problems were mostly focusing on
yeah, that's all that you're focusing on. So there's nothing more. There is one. Okay, so I already put 3 problems out there. One of them was just a simple, box that's being shoved, I think, to the right. There's 2 of them that have the pulleys. One of them simpler than the other, but both of them about the same level. And that's it for this week. What I was going to do is I just looked and, there's the normal and tangential component thing. And I think those are okay. Although most of the time those are dealing with like a ski jumper that comes down and his, like normal acceleration is a certain amount. And then it's like, how much weight is he having to hold up? Well, all you're doing is you're taking mg and adding the acceleration comes in. So I think those are okay. They're oversimplified. But what I do want to touch on, so I'm going to skip that one, is what I'm getting at, because that one kind of is a subset of this one. And for some reason, he put an asterisk on this now. So before, he didn't think that, but now he's saying this is what does he call it? Optional section, he thinks, the Arthur thinks. But I think it's kind of beneficial. So, that's why next week I'm going to give us like probably one bigger problem or two smaller ones on this. There'll be enough there. So that's it. That's all. This is all F is equal to MA. And you already figure out how to do A in chapter 12. So all you're doing now is you're doing an object, the the mass, whatever, the on the pulleys, and you're doing a free body diagram off of it. That's all that's being added here. But this one is particularly annoying, and that's why I like to cover it. He goes through, he comes up. I'm sorry, I'm gonna probably be coughing a lot, but um, he comes up with this. Often that Z component doesn't even exist because it's in 2D. Here's the part that to me is kind of strange. Okay, so he has this thing set up so you can see these are kind of repeats, the diagram. What he has is he says, okay, a marble, say, right here is traveling along this blue path and it has a tangent. Okay, and what he's going to do is he's going to do something really bizarre, I think. And that's okay, but it's also, you're already doing something else that fits this. So he says, okay, you may be pushing it with this P, and maybe there's some sort of force here slowing it down, and there's some sort of normal force making it turn up the blue path. And he says, here's the tangent. Then he comes over to this other diagram, and he comes up with this funny angle right here. And then he comes down another little bit, and he talks about this angle. Then he comes down and he says, okay, here's a funny looking diagram. And you look at that and you're like, okay, I kind of see that, but there's a lot going on. Then he goes down and he comes up with that. And you look at that and I say, so if you can find that angle, well, the part that to me seems so bizarre about this approach is you're adding complexity to something that you already know what to do. That tangent is essentially the direction of the velocity. That's all it is. And so if you can find your velocity, which, by the way, is easier than finding your acceleration, you can break it into components. You can find that vector going in that direction. And that's beneficial. If you've got that, you can break it into polar coordinates in the r and theta, er and e theta, and you have all that. But why would you go do extra strangeness if you already have that? So what I want to try to do, I don't think I'll be able to complete that today, but I want to kind of do a problem that kind of accentuate that a little bit. Actually, if he's got a good problem in the next, let's see, maybe he's got a good problem, and I could just do it off of that. Because then I could compare to his approach. Okay, did I click that? It's not. Hello? Hello, machine. Okay. Uh-oh, what did I do? Oh, something happened. I may have gone forward. I'm not sure. Let's just be patient a second. It's possible that he has an example with that in there. And if he does, I'll do the problem, the other approach, so you can see the difference between the two. But first, the thing, okay. He does have that. Okay, let's see. Oh, that seems reasonable enough. I mean, maybe the next problem might be better, but it might take a week for me to bring it up. Okay, so he's got that. Okay, so here's acceleration R. There's his F and NC. But does this thing have no mass? Does that little doodad have no mass? Okay, a smooth half a kilogram can slide freely on the arm, on this thing, and the circular guide rod. So this little part. If the arm rotates with a constant in that, determine the force the arm exerts on the collar at the instant of 45 degrees. Come on, that's too easy because it's going straight up and down. Okay, so I might skip this one because the tangent line is straight that way. That's not complicated enough. So we'll look at the next one. I want one that you have to find that tangent. Okay, so here's a wheelie thing. 2 kilogram cylinder right there. Has a pin through it, and it passes through that slot. Okay. If the arm is forced to rotate in the vertical plane at a constant rate of that, determine the force the arm exerts on the peg. I think we got the same problem here. So the path of this thing is going straight to the right. The velocity of the wheel, the 2 kilogram thing, is going straight to the right. So it doesn't have a particular path. It makes it simple. It's not having to find that. So this one doesn't even have that, because the tangent of this thing, the marble, the cylinder, its path is straight across there. It isn't out there in space. So let me see if we got another one. So he's given us 2 easier ones. Let's see. Oh, this one might have it. Okay. Unless he's going to do it right at this plane. But then, even then, you got the tangent that's going to go in this direction. A and C have a mass of half a kilogram. Moves along the grooved horizontal slot. Okay, horizontal slot in the form of a spiral. So this is his spiral, this little blue. I guess that's defined by the equation that, where that's in radians. If the arm rotates at a constant rate of that, determine the force it exerts on, determine the force it exerts on the can, what's the can, at the angle. Oh, well, okay, neglect the friction and the size of the can. I'm guessing that he's saying that thing is a can. Did he use the term? Where did he use the? Oh, okay. A can C. Okay. Okay, when I saw that, I'm sitting there looking at the A, seeing the capital A, and then seeing the C, and I just skipped over the word can. Okay. So it is a can, not the letter A identifying. Okay. So here he does this. This is the part we're going to do a little bit different. So let's go ahead and do the first part of this. And then that's finding the, that's funny, the acceleration of this along these lines. So let's see if I can do a snip. Oh, shoot. Okay, there we go. There we go. And let's see if I do have, I should have space here. Drop it right there. And oh yeah, it is right here. So he has this right here. So he tells me that, and he told me that that's constant. So this is the case. Since that is constant. So you got those 2 things right off. Then you got this, r is equal to 0.1 theta. So then you're looking for dr dt, which is nothing more than dr d theta dt, which is nothing more than, that's pretty easy to take that derivative, because it just becomes, sorry, it just becomes 0.1. I guess I've got to put, yeah, because he just puts that in there. Times theta dot, and that theta dot came from right there. So then you're looking for dr dt squared, or, you know, this is sometimes written that way, and this is sometimes written this way. So it just so happens that this thing becomes, oops, hang on, that becomes 0.1 theta dot, which which becomes, the 0.1 can be sucked out, and then you get theta double dot. But that thing was 0 to begin with. So let's see if I can sort of patchwork all this together in a good way here. R is equal to 0.1 theta. R dot is equal to 0.1 theta dot. R double dot is equal to, you take a derivative of that. I should have put the equal to 0 sign there. And then I got, okay, theta, which he, I think, defines that when it's totally vertical, not vertical, horizontal. So he's saying that theta is equal to pi. And then he says theta dot is equal to, what did he say, 4. Theta double dot is equal to nothing. He did say it was constant, didn't he? I better check that. Okay. Rotates at a constant rate of that. Oops, that's wrong. Okay, so I think I've got all that. Then, I know I'm not supposed to, if you look back, and I'll even, here, I'll do it this way. I don't think oh, I did have that launched. Wait a minute. I do have this launched. Let's do this real quick. I think velocity, I think I misspelled it. There you go. It's a good thing that, now there is a, there it is. I used to reference this, and put it in the thing. I could reference it again. This is a paper that, not a paper, a lecture that they had years and years ago. Just the only difference is he has an ER here, E theta, and he goes through the whole thing. Comes up with the velocities, which these things should stay the same. So velocity equals to R. First we'll do velocity, because unlike what R dot, UR plus R theta dot, U theta, and then acceleration is a little bit more complex. And that's it right there. You know what? I can't do any better typesetting than he can. So there you go. We'll just do that. And then I can get rid of mine. Okay. So in his and ours, the only difference is these are the same things. He's used a base vector and called it ER instead of UR. That's the only difference. So if I'm looking for the velocity, and you really, quote unquote, are not necessarily trying to find it, but here's what you'll find out. R dot, if I go over here, you go over here, take that and put it in here, I get 0.1, and then I get that 4 because I copied this 4 back over into here and put it right in there. And if I do that, I get that UR plus R, 0.1, and it's theta, so you put a pi here and you put that right there, 0.1 times pi. So that in fact becomes R. And then the theta dot just gets copied, U theta. Now, I've been doing this in other classes, and I think I did this in here. Okay, so let's see. I think I know how to do that. The other thing is, I think I want to go ahead and do this into a numeric thing. 3.14159 times 0.1 times 4 gives me 1.2566636 u theta. Now, I'm a little concerned about this. And the reason I'm concerned is because I think, okay, if I think about this, okay, let's take this picture and recopy it. And I'm gonna just put it in there. Let's see, did I copy everything down at 4 to 0.1, and it was at pi. So technically, if his drawing is reasonable, here, let's do it this way. Here. Just kind of mimicking this. This would be the velocity. Now, hang on. This would be UR, and this would be, hang on. This would be, okay, U theta. Okay, so does it seem reasonable that I would get, and get rid of the ruler, I would get 0.1 would be the magnitude in that direction, and 1.25 and some extra digits would be the magnitude in that direction. And I don't know, it looks to be reasonable. But by doing that, I've already determined what the tangent direction is. Okay, so then the next thing so this is my side issue. So my side issue is that I'm going to basically find the tangent off of this. So I'll put it to the side, and then I'll say, I'm going to come back to it. I hope I'm making sense. That this is how I'm going to find the tangent in a second. And when you find the tangent, and I'll have to redraw this and maybe explode it a little bit, I'll be able to find the force component normal to that tangent, which I'll do in a minute. So in this next part, I'll go ahead and do the accelerations r double dot, which that's easy enough, 0 minus r, which is this times that, to be 0.1 times pi, and then theta dot squared. Theta dot squared would be just 4 squared, and this would be, okay, I'll go ahead and keep our base vector notation. R, that's fine, but theta dot's 0, so I'll just say r times 0. And so this will be gone, that'll be gone, this will be gone. Okay, plus 2 times r dot. R dot was this times that, stuck right there. 0.1 times 4. Okay, 2 times r dot. And then I got r dot again to be 4 again, and u theta. So I get minus, all right, well, I'll try a reasonable, okay, 4 times 4 is 16 times 0.1 times 3.4159, about 0.026. I'm carrying too many digits, plus all this stuff. That's 16 times 2 times 0.1. Let me know if I'm making a mistake anywhere. Okay, so there's my acceleration. So I've got that. So the next thing I'm supposed to do is I'm supposed to do this. I'm supposed to do sum of the forces in, say, I don't know, r direction is equal to mass times acceleration in the r. And that'll be that term. And then I've got to do sum of the forces in the theta directions times the mass times acceleration in theta, which is that. But I've got to do a free body diagram somehow so that I get these two components out. So it's convenient in the sense that this kind of goes along to the left and this kind of goes down. But what I really need to do is this. Let me go back to the book. I probably should take a little check on myself first, but I'm going to zoom way in as much as I can on that. I'm going to copy the thing. Okay, I think he said it was in the horizontal plane. When he's saying that, that kind of means the gravity's pulling that way. So I'm looking down at it. The gravity's just keeping the thing in the track. That's kind of all it's doing. So there's no gravity force. I think that was what was said. But I'm going to have to check back at that. So, what are my forces? I got two general forces here. I got a force that this little blue arm is pushing on the ball. I probably shouldn't just make the thing bigger or something here. Here, let's do like that. We'll drag out a ruler. So they're not showing that they're touching each other, but they actually should be touching each other. So this thing is pushing, I don't know, with F1. I don't know. And then this thing, the little rack. Okay, so just out of curiosity, I'm going to do something here. I'm probably going to erase this in a second. I had a tangent. It was kind of like, that looks like close enough to the tangent. Actually, maybe tilting it like that. So let's do this. This is kind of along the tangent. Okay, I meant to not do that. Is it not? Okay. So this is kind of the tangent. Okay, so there's your kind of your tangent, which we got from the velocity. But then the little, okay, I'm just going to try my best to do a reasonable job of making these. That's reasonably, so that is the, so in other words, this to this is 90 degrees. So in fact, I think what he will probably say, and we're going to check that his free body diagram and mine look the same. And I'm probably going to change my subscripts to his. Okay, so that's F2. I don't know what he calls those. So let's go back and look and see what he calls those. So first let's look at what he did. His solution. He came up with that. There's his drawing over to the left. Then he's got his tangent. He's got an NC. Okay, so he put an NC going that way and an FC going down that way. Naturally, I think I would be more comfortable making the NC go in, but I'm just doing it the opposite direction of him. If mine comes up to be negative, then mine goes in his direction, and that's fine. So he's going to find this angle right here, that thing right there. And so the way he's going to do that, it's kind of like, let's see what he does. He goes down and does something like that. Okay, then he comes back. Okay, wait a minute. What? That's his. That symbol. Where is that thing? Oh, okay. He's saying that's 17. Okay. So here's what he's saying. That angle is 17.7 degrees. And he's used this weird formula, which is okay. If you can look at that and understand that and like to use that, that's fine. But let's see, compare what it is that ours is. That wasn't what I wanted to do either. So he's saying this is 17 degrees. Let's see if we can get this out of this. Okay, so if I have a triangle, so if I go in and take a look at this, and I go ahead and copy this over and say, let's just do it this way. Well, I can just do it on the drawing itself. So I have a vector that goes out here. Its length is 1.25 6636. I don't know where that ended up. 2.56636. And the other one I think was just 0.1. Yeah. So I can do this one of two ways. So essentially I just have a triangle that looks like this. 0.1 there. And 1.256636. I can find that's 0.1 as well. I can go in here just, I mean, I know you can do the tangent, but just as a case in point here, I'll just do this way. The length is equal to the square root 0.1 squared plus 1.2552636 squared. And what I'm going to do, I'm going to see if this photo math will calculate that for me. If I can get the picture, if I did a reasonable job there. Let's see if it'll recognize that. I did. Okay, so this is about 1.26061. So if I want to find that angle, I can do it two ways. You can do a cosine or a sine or a tangent. I don't know. Let's see, sine of, I think he had that symbol as that, is equal to 0.1 over 1.26061. So I'm going to see if photomath will figure that out for us. Sine inverse. This will be interesting. 0.1 over 1.26061. Let's see. Take a new picture. I have no idea if it'll find this thing. It did. Wait a minute. What? That I don't believe. He did that in a weird way. Okay. That's not. I so that I don't believe that. So I'm going to use the calculator. 0.1 divided by 1.26061 gives me that. Then how the heck do I second? And then sine? I have 4.5498. Is that what you got? Okay, so let's look back and see if I did anything wrong. First of all, let me see if I've got the same. Let me check, see if I got the same accelerations that he got. Although they're not related, they could be thought of as being related. Okay, equations of motion. Yeah. So, oh, here we go. Kinematics. So I got that. I get this. So 0.4, is that what I got for the R dot? Well, yeah, because if you take this, here, get rid of that. If you take that 4 and stick in here, you end up with 0.4. So we got the same thing there. Did we get at the instant of that, you got minus 5.03 and 3.2. Okay, minus 5 point, that's close, and 3.2. So those are reasonable. Now, okay, substitute those to get the answer. Now, what does the negative NC mean? Okay, so that means it flipped over to make the thing turn, so that's okay. So the question is, what did I do wrong on the velocities? Because there's no other solution there. Okay. So let's see. R dot. Oh. What the heck? How did I do that? Okay. That is a 0.4. I don't see how 0.1 times 4 is equal to 0.1. So somehow I goofed that up big time. And then this one should be using photo math. Just out of curiosity, I'm going to do that on this. Well, I can't fit it in the can't fit it in the picture. Let's try that. Let's see what it'll do there. Okay. What? Oh, yeah, 1.25664. Okay, yeah. Cool. Okay. So now, let me fix that. Okay, so I got to change this. Oh, God. The 4. Then that's definitely not it. Let's see. Let's let Photomath figure that one out. That's 1.31876. Now, I had trouble figuring out how to get that to work, so on Photomath, so I have to do this one by hand. Okay, so let me go in there. Y'all probably could get it quicker than I can. Is that what it is? 17.656. Okay. So I think, man, where did his answer come? Where did I find it? It was in here. Okay, 17.7 is what he got. So we got the same answer given the fact that I didn't make that stupid mistake up there. So in fact, okay, to me, this approach seems much more logical because once you find the tangent, you can find this angle. For that matter, at this point, if you found it necessary, you might find it more necessary to find this angle. And instead of just plugging in a formula that just happens to be presented to you, I think this is a better approach because it makes more common sense. The velocity is the tangent, and it can orient things that way. So what happens now, no one cares about this one. Okay, so here's what I mean. Let's do sum of the forces in, this is u theta. So let's do them in the theta direction. Equals to mass, which I think this thing was 2 kilograms, or maybe I'm got that wrong. No, it's a half a kilogram. Times the acceleration in theta. So that will be a half. And I think, what was the acceleration in theta? Theta was 3.2. So 3.2. Dang, man. And over here I got two forces. Okay, I'm going to try to line mine up with the same symbols he's got. He said one was FC and one is NC. Okay, so I'm going to go back and change that. I'm going to change that, call it NC. Here, just to be, this is NC, and this was FC. I just called them F1 and F2. It really doesn't matter what you call them. But now I've got a force in the theta direction that is going directly in the theta direction. So it's a plus FC, and I don't know what it is. But then I got this one. Okay, this thing has to be broken into its components, and that's where this theta, I say theta, whatever that tangent angle was, the 17 degrees, 17.656. That's where that came in, because in essence, this NC can be broken into a coordinate, into a component in that direction, into a component in this direction. And that's the 17.656. Why is it that way? Because if you think about it, this is perpendicular to that, and this one is perpendicular to that one. So the fact that, you think about it, you had two 90-degree things, and one just rotated a little bit, and essentially that that's why that angle is that. So what you get, this component is going down, which is positive, and it is MC, and now it is sine of, okay, 17.656, and that's that way. So I get one equation here. Now in he's going to have that being a negative because he's pointed it the other direction. And then I've got to do one more, and that's sum of the forces in the R direction. You go times acceleration in the R. Now that one was the -5. I'll go ahead and do his minus 5.03. I'm fine with that. I don't want to cough up anymore. Okay, and it was a half. And now, dang. Now, I get this component going to the right, but this was the direction of UR. So this thing, this NC, is NC cosine of 17.656, but it's going to the right here, and the positive direction is to the left. So that becomes a minus. And that's your other equation. Now, if I wanted to, I bet you I could say NC is equal to 0.5. Let's just do this. 5.03 divided by cosine. Okay, now this photomath is going to get upset at this because it thinks everything in there is in radians. So I'm going to do something weird. What I'm going to do, I'll say times pi divided by 180. And let's see what photomath does with that. Interesting. First of all, does it recognize it? I think it recognized everything. And it gets a value of 2.63933. The question is, okay, what I got NC at 2.64. That's what that is. Yeah, so hang on, sorry about this. One day I'm gonna get over this. So I got the same answer. So his is 2.64. His is a negative because he assumed it the other direction. If I want to, I can take that NC and stick back up in here and take this around and say FC is equal to, okay, 0.5 times 3.2 minus 2.64. I'm just going to times sine of 17.656 times pi over 180. And let's see if photomath can figure that one out. But that arrow is going to be in the way. So here, come back far enough away. 3.2, 2.64 sine of, and that's pi over 80. It gets 0.799 284. Gosh, I'm coughing on the screen. Okay, 0.8. Yeah, that's close enough to 0.8. But I think the key for me on this one, and it's up to you what you want to do. The key for me that I never have accepted. And so this, and I've accepted in the fact that it's the right answer. But when I look at that equation, it just seems so obtuse to me. It seems so weird, given the fact that earlier in the text, and something you already know, that the velocity is always tangent to the path. And this is working off the tangent to the path. So the fact that you have a velocity and you can find a velocity, now, you know, I have the general equation for the tangent to the path. So, you know, to me, that makes better sense. So, so use what you think you would rather do, but I don't I don't know why this was stuck in there that way. It's been stuck in these things for years. This is the 15th edition of this book. I think this equation's been stuck in there at least since the 8th edition. And so to me, if you go to a physicist and ask them, they're going to say, find the tangent to the path, and that's the velocity. And then that'll have your direction, and then you can use that. That's what they're going to tell you. So it makes better sense. I don't know. But there are some people that will just use the equation because it was put there. So, I'm sorry, I'm coughing. At least I'm more than 6 foot from you. And I don't think I'm infectious anymore. I don't think. I hope I'm not.